Midas NFX Simulation Lecture 2 Model Analysis or Natural Vibration Problems. And we're going to solve a problem of a cantilever beam 10 meters long and with a cross-sectional area of 5 centimeter by 5 centimeter or 50 by 50 millimeters. So this is the beam, and we save the file as a parasolid file, and then we enter NFX and open a case, and we name it 002 and import the geometry as a parasolid file. So now we have finished with the first step by opening a case and importing or drawing a 3D model, the geometry step. The second step will be the material. So we load the material, isotropic material, 1020 mild steel, and I'll change the Young's modulus to be 3 times 10 to the 11 and Poisson's ratio of 0.3 to make easier my calculations. And in this way, the natural frequency theoretical value will be 0.49 for the first mode, and the second mode was 3.14. So we can confirm the result. So this is the loading of material. Then we need to connect the material with the geometry. There's only one object, so we simply change the material into 1020 mild steel. And we have finished with the second step, the definition of material to the 3D model. And for the third step, we'll mesh the geometry. So we select the object, and then we'll define the size of the mesh and perform the meshing. So this is the third step. And we can hide the mesh or show the mesh. I'll let it show for now. For the fourth step, we can apply constraints or boundary conditions here. You don't have to apply boundary conditions in this problem, but it is a more straightforward way, because we always see that a cantilever beam is fixed at one end. So we'll totally fix the right hand side surface of the beam. So this is the step 4, and actually it is the part 1 of step 4, right, for statics analysis. And there's also loading procedures, but in a model analysis or natural vibration analysis, the external force is ignored by the procedure because it is located at the right hand side of the equation, of the ordinary differential equation. So it is ignored. So we don't have to apply any external force. Even if you apply an external force, it will be ignored by the procedure. But in one case where the internal stress is built up so that the rigidity of the structure increases, which will increase also the frequency of the structure. But in this case, we are not going to apply force. So for the fourth step, we apply only the boundary condition fixed end. So up to now, we have finished with the step 1 through step 4, or the preprocessors, and the problem is fully defined up to this point. So we can go ahead and proceed with step 5. So now we will include a model analysis, and here we will edit the content of eigenvalue and make it calculate 15 modes and frequencies. The default is 10 frequencies, and I'll make it 15 so you know how to change the number of frequencies to calculate. So we can proceed with calculation and save the file. and we have finished with the calculation. So the eigenvalues will be 0.49 for the first mode, 0.49, right? The second mode would be 3.12, and the theoretical value is 3.14. It is very close. So these numbers are theoretical values calculated from solid mechanics or mechanics of materials. But look at here. If you look at the third mode of vibration, it is 8.7. And the theoretical value by mechanics of material, it will be 10.6. It is deviated by about 20%. Look at the fourth mode. The fourth mode would be 17.1 in 3D model calculation, CA analysis. And for theoretical value, it is 30.8. It is about maybe 45% deviation. So you know from here the result that the CA result deviates from the theoretical value when the mode shape get higher and higher, right? But it is a very precise calculation for lower vibrational modes. The reason is that in solid mechanics or mechanics of materials, we calculate the cantilever beam with a neutral axis. It is one-dimensional simulation to the three-dimensional geometry. But in CAE analysis, in model analysis in CAE, we use 3D models instead of only one line. So this is a simulation using only a single line to simulate a 3D geometry. So in lower modes, it is correct, but in higher frequencies, it is not correct. So the real answer is the 3D result. So whatever software you use to calculate this result will be the same, but it is deviated from theoretical value. But again here, the theoretical value is not precisely right because it is a simplified model using one line, a neutral axis simulation. So this is the correct answer. This is the second lecture of Midas NFX.